Warm welcome to everyone joining. Thank you for being here. Go ahead and get yourself ready with a notebook. Grab a pencil or pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have an introduction to implicit curves. Yes, that's right. Implicit curves. They do not define a function. They don't follow the rules for a function. But they have graphs, they have equations, just like functions do. And in fact, we call them a relation whenever there is a relationship between x and y or some other variables. But it's just not a function, because, of course, a function requires one output for every input, whereas a relation can take many outputs for a given input. Now, I have a few questions regarding this relation. These are easier questions than what you're going to see in calculus, no doubt. But I want you to get used to seeing these kinds of equations with x and y in it. And the y is not just in one place, it's kind of all over the place here, right? So go ahead and take a look at these parts. I have 3 questions regarding this relation. Give yourself, I don't know, maybe about 7 or so minutes to work on this on your own. Then when you're ready, after you've tried your might, come on back and see how we did it here. Okay, now we're going to consider this relation 4x squared plus 3xy plus y squared equals to 12. Great. And the first question is asking us about the x and y intercepts, which is really just such an important skill that you should have from algebra, but I need to make sure that you're solid with it now and that you recognize how useful and how simple it is to figure out x and y intercepts sometimes. Remembering that for the x-intercept, we simply need to just make y equal to 0. And that immediately simplifies our equation quite a lot. It turns this into 4x squared plus 3x times 0, so just nothing, that's just 0, plus 0 squared, and that equals 12. Okay, easy enough. So 4x squared equals 12. We can really easily do the math on that. That means x squared is 3. And this means that x equals plus or minus square root 3. Remember, this is important. Whenever you use a square root, an even, I'll even highlight it, even radical, to solve an equation, you must consider plus minus, always, every single time. And especially because in this case, we have multiple y values that could exist for a given x value. We'll also want to do this when we're solving an equation with y's in it. So there are our x-intercepts. We have 2 of them. We have negative square root of 3 comma 0 and positive square root of 3 comma 0. Great. Now let's find the y-intercepts. For a y-intercept, we want to make x equal to 0, which again simplifies a lot of the equation. We get 0 plus 3 times 0 times y, that's a 0, plus y squared equals 12. And that is really easy indeed. That means that y is simply plus or minus square root of 12. And let's just go ahead and simplify that expression. Plus or minus 2 square root of 3. So we have 2 y-intercepts when x equals 0. That would not be valid for a function, but since we have a relation, we're allowed to have 2 y values for the same x value. This would not work for a function, but it does work for the graph of some relation. So there are the x and y intercepts. Beautiful. Got my x-intercepts right here. Got my y-intercepts right here. And you could get a few points on the graph already. I sense symmetry, don't you? These x and y-intercepts are symmetric. Doesn't mean the whole graph is symmetric in any way in particular, but we have this symmetry of their locations. Okay, let's look at part B. It says solve for y in terms of x. And this is a little bit tricky if you're not careful because there are 2 variables here. But we're going to treat x kind of like a little rag doll, like a test dummy. When it says in terms of x, it just means move it around however you need to. Move it around as if it were a fixed value, like a constant. You can just treat it like a 2 or like a times 3. Just move it around like a constant. If you need to divide it, throw it around. I should also say move it around like a coefficient. It sort of acts as a coefficient, and that makes it a lot easier to understand how to work with this. Because here we have 4x squared. That's a constant. Even though it has a variable in it, when we're working in terms of x, it's not the key variable that we're trying to isolate. We're trying to isolate the y. Plus 3xy, so it's kind of like that's the coefficient on the y. And then we have y squared, which is the typical squared term. And this equals 12. So we're going to have to move everything to one side. And you'll notice that this is basically quadratic. It's like we have 1y squared plus 3xy. Remember, x is being treated just like a regular number here. It's not being treated like a variable because we're isolating the variable y. So everything else gets treated like it's not a variable. And then we have this constant, but the constant is going to be 4x squared minus 12. That's all one constant together. And this equals 0. So now this is basically a quadratic equation. Yeah. And to solve a quadratic equation, we could try to factor this if you'd like to find two expressions who multiply. You know, their product is 4x squared minus 12, and their sum is 3x. I wouldn't really volunteer for this. I would elect the quadratic equation, the quadratic formula here. So we're going to use negative b, that's negative 3x, plus or minus. You see, this is the a and c, which would normally be our coefficients on the x and x squared and the constant term. But again, because we're using y as our variable here, we're treating it like anything in front of it is the coefficient. So negative 3x plus or minus the square root of 3x all squared, not just 3x squared, 3x times 3x. Be very careful with this kind of a step. Plugging in 3x, this is not the same thing as 3x squared, just to be clear. Minus 4 times a, it's easy, times c, that's still not bad. And this is all over 2a. All right, we have a little bit of cleaning up to do on the inside of this radical here, right? Let's clean all of this stuff up. So, of course, that's going to make 9x squared minus 4 times 4x squared is 16x squared, and negative 4 times negative 12 is a plus 48. So that's all the action that we got going on inside of this square root. Lots of action down there. And we can simplify this even further, my goodness, to negative 7x squared plus 48. This is all going to be over 2. Okay, great. Now, this is two different answers, mind you. On one hand, we have negative 3x minus this interesting square root expression all over 2. And then on the other hand, I have negative 3x plus the square root expression, negative 7x squared. I put a minus on that one, didn't I? Whoops. All over 2. And these represent two pieces. These are two related but distinct pieces of the relation. They are each functions of x. I think that's just the best way to say it. They're each a function of x. And they cover the same domain. That's really what's important, because that's going to lead us into the next question. The y value is either given by this equation or the y value is given by this equation. But in both cases, we have a restriction on the x value. So we want to find out for which x values is y real valued, meaning when does y actually have a value? Well, regardless of whether we have negative 3x minus the square root expression over 2, or if we have negative 3x plus, either way, this is only a real value when the inside of the square root is non-negative, because remember that a domain restriction on radicals is that the inside of the square root cannot be negative, right? So let's see what values that would entail. So we would need 48 minus 7x squared to be greater than or equal to 0, which means we need 48 greater than or equal to 7x squared. And therefore we need 48 over 7 to be greater than or equal to x squared. This means that x can be a really big negative number, or it can be, x needs to be a really small negative number or a really small positive number, because its square cannot exceed 48 over 7. So it needs to be somewhere in between the negative square root of 48 over 7, which I'm not sure what that is. It's very close to 2.6, and positive square root of 48 over 7. Those are the values that are going to give us real y values for our relation. Otherwise, the inside of the square root will be negative, and we won't have any real y values. Okay, there wasn't too much heavy algebra here, to be honest. We did have to use the insight of treating x like a constant or a coefficient when solving for y. And we also needed to recall the quadratic formula, but that should be all the bread and butter that needed to go along with this meal. I'm introducing you to this concept of implicit curves because you've spent so much time learning about functions, and I'm so proud of you, really, I am. However, calculus is a bit of a beast, and it doesn't just regard functions. You don't just analyze functions, you also analyze equations like this, and you'll have to be very comfortable with doing that. So it's a great idea to get introduced to this stuff now, before it gets too intense. I think that's enough blab out of me. I highlighted the most important points of the problem. I'll see you guys